Let's look at heat engines. Specifically, I want to talk about the Carnot cycle here. Remember that with a heat engine, the basic idea is that we want to expand, we want the piston to move out at high pressure, and then we want it to move back in at a lower pressure. Okay. Now, this is Sadi Carnot, and what the Carnot cycle is famous for. No engines actually can do the Carnot cycle. But what he did was he said, look, if a heat engine followed this path, it would achieve the maximum theoretical efficiency. Okay, here's the basic idea, right? Is that we have a high temperature and a low temperature. We do our expanding at the high temperature, at a high pressure, right? And then we do our compression at a lower temperature. And that gives us area inside of our little PV diagram, our cycle, right? And you understand that that's the work, the net work done by the cycle, right? Now, basically, if you want to make this thing more efficient, you want the high temperature to be higher, the low temperature to be lower. That will expand this little area there and give us more work, okay? And you can look at this, right? You can see that as the cold temperature gets colder and the hot temperature gets hotter, mathematically, the Carnot efficiency approaches 1, okay? And there we have it, right? Sadi Carnot, by the way, lived only 36 years. Imagine if he'd lived a bit longer, right? He died in a cholera epidemic of all things. All right, so here is our Carnot cycle. Typically, we start in the upper left-hand corner here, but understand, what we got to understand, these lines right here, these are isotherms. Okay, this guy is hot, this guy is cold. How do I know it's hot and cold? Well, for given this is the same amount of gas, right? Here I've got more pressure and more volume. It must be a higher temperature than this one all along, right? Remember that these isotherms obey this rule, right? Pressure times volume is pressure times volume, right? So as we increase our volume, as we move our piston out, and the temperature remains constant, as we give the particles more room to run around in, the pressure drops, and that's what's happening here, right? Or conversely, if we give it less room, the pressure will rise. Okay, so let's just go through this cycle here and look at the heat transfer and all this. Okay, so there are 4 processes. The first one is from 1 to 2. Okay, along this path. This is an isothermal expansion. We know it's an expansion because the piston is moving that way, right? Notice that the pressure drops because we're just giving it more room to run around in, right? Okay. In an isothermal expansion, remember this is a constant temperature. It follows this temperature path. This is the high temperature. Here's the lower temperature, right? And so we can do our little equation here, right? Our Q is delta U plus work, right? We know that the piston moves out. We know that that's positive work, right? Piston moves out, okay? We know that the internal energy does not change because the temperature doesn't change. It's constant temperature, right? And so if the temperature doesn't change, the kinetic energy of the particles doesn't change, the internal energy doesn't change, right? And so therefore heat has to flow in, and this is the famous heat that flows in from the boiler. That's what their little diagram here is, this Q thing here, right? They're calling it Q1, we might call it QH, okay? The heat from the boiler, right, flows into the gas. It expands, the heat turns directly into work, okay? Notice that in this case, the temperature is constant. We follow this little path like that, okay? The next thing that happens is, we've got to get the temperature to drop because we need to follow a different path back. That's to create area inside of our graph, right? So the best way, and this is, the theoretical best way, Carnot actually figured this out and proved that this is the most efficient way, right, is to do an adiabatic expansion, right? Notice that in expansions, the piston moves away from the particles. When the particles bounce off the piston, they come off slower. The temperature goes from high temperature to low temperature, okay? So here the temperature is going to drop along that process. Remember that adiabatic processes follow steeper paths because the temperature changes, right? Okay, so in an adiabatic expansion, we've got Q is delta U plus work. Well, we know that the piston moves out, right? So that's positive work. Okay, the heat flow is 0. And so if we have positive work, the only way to have that happen is to have a negative change in internal energy. Okay, so macroscopically, conservation of energy, right? Here the temperature falls, right? And we go from the high temperature to the low temperature like this. Okay, so our next process, the next exciting process is from 3 to 4, right? We're going to go from here to here, right? And basically, Sadi Carnot is just trying to get back to the original starting spot. He's trying to follow these processes, right? Isothermal and adiabatic. And the cool thing about these processes is that they are isoentropic. Now, if you've been paying attention in class, iso means it's the same in the entropy. So basically, this just means that the entropy does not change. Okay, we'll talk about why that is when we get into calculating entropy. It's a fairly abstract concept here, but the fact that the entropy doesn't change makes this reversible, and Carnot proved that achieves the maximum theoretical efficiency, right? So remember, no real engine actually does this, where this is just a theoretical process that's very, very important to the IB and lots of people that study thermodynamics, okay? So now we're going to get back, we're going to do an isothermal compression. Remember, this is, the piston moves in, but somehow it moves so slowly that it doesn't change the temperature of the gas particles, right? So this would take a long, long time. In fact, it would actually take forever. Okay, so that's why these are isothermal processes are fairly theoretical, at least, right? Okay, so let's do our little thing. So Q is delta U plus the work, and notice that the piston's moving in this time, right? So our work is negative, work done on the gas, right? Okay, and then we also know that since it's isothermal, that there is no change in internal energy, right? And so therefore, it must be that heat flows out of the gas. Remember, negative Q is heat flowing out of the gas, right? So this is the famous waste heat, okay? We will call it QL or QC, and since my handwriting's so terrible, you can't tell the difference between it, right? So the heat that flows out of the heat engine is wasted, right? In New York City, the steam plants that generate electricity actually use that steam, which is not hot enough to be used by turbines, but is warm enough to heat apartments. They actually use that to heat apartments. Sometimes, like nuclear power plants, I believe, just vent it to the atmosphere, or the heat is put in rivers where it heats the rivers to unacceptably warm levels, right? Anyway, so there we have it, right? Our final step now is, of course, if we want to increase the temperature and get the piston back to where it is, we do that adiabatically, okay? And these are not just arbitrary spots. There is a particular spot here that the adiabatic process, when it goes from here to here, right, it actually intersects that line. It's not where we decide to change from this to this is random. We just decide at some point, hey, let's go to adiabatic, right? And then coming back, this has got to be figured out exactly where we start to do that, okay? An adiabatic compression here, remember that the heat flow is zero. It's a rapid process, right? These guys are fast, these guys are slow, right? And for this guy, Q is delta U plus the work, right? We know that the work is negative because we're pushing the piston in. We know that heat does not flow in or out of the gas, and so therefore the internal energy must rise, okay? You also know that the piston's moving toward the gas, right? And as the gas particles bounce off, they bounce off going faster, and so it heats it up, and we get back to our original temperature and our original position of the piston, okay? So key concept here, you have to have two different temperatures to get work out. You've got to have a hot temperature and a cold temperature, okay? And as those hot and cold temperatures diverge, the efficiency increases. So a bigger temperature difference gives us a bigger efficiency, right? And then, finally, the only way, this is the Carnot efficiency, right? The only way to achieve 100% efficiency is to actually have 0 kelvins as your cold temperature. And then, the sad story is that the third law, one of the ways to state it is that no object can actually reach absolute zero. So therefore, it's not possible to turn all of a particular amount of heat into the discrete energy of, say, a turning flywheel or a moving piston, because that would actually violate the second law of thermodynamics.